First two speakers this afternoon will be talking on Fischer-Tropsch catalyst, iron Fischer-Tropsch catalyst, and our third speaker will address the subject of dehydrogenation of nickel sulfide catalysts. You'll see as you looked in the session this morning as well as this afternoon that we continued our theme of not only looking at deactivation but also regeneration of catalysts. And our first speaker this afternoon is Scott Eliason from Brigham Young University. And he will be talking to us on the kinetics of deactivation by carbon of iron Fischer-Tropsch catalysts. Scott.
Thank you. All right. Well, it's a pleasure for me to meet with you today. Can everybody hear me all right?
Yes.
At our catalysis laboratory at BYU, we've been studying Fischer-Tropsch on iron, and today I'd like to give some information about the kinetics of the deactivation by carbon on those catalysts. The objectives of this work were to obtain kinetic and deactivation rate data as functions of temperature and reactant concentrations on unpromoted iron catalysts at high pressure. In this work, high pressure refers to 10 atmospheres. Since both the hydrocarbon product and the deactivating carbon all originate from the CO in the gas phase and possibly through the same surface carbon intermediate, it's necessary that we obtain reaction rate data at conditions where deactivation is not occurring. And then it may be possible to decouple those where rates of both reaction and deactivation are significant. Second part was to calculate reaction and deactivation orders in the power law expressions to give us an idea of what effects the different reactants have on the reaction rates. And also, in terms of the deactivation expression, there's also included an activity and an order of deactivation, the M power there. This rate, deactivation rate, is simply the change in activity with time. And then lastly, develop a model for the kinetics, which is consistent with the data. Briefly, the catalysts were prepared by decomposing iron nitrate with some aluminum nitrate at 120 degrees until it was dry. This was followed by calcination at 200 and then crushed into a powder. This powder was mixed with water and slurried onto monoliths with 300 channels per square inch. Several applications being required to obtain the desired 1 to 1.5 grams of catalyst per monolith. And in each case, the samples were reduced at 400 in flowing hydrogen prior to reaction. Conditions of the experiments are shown here. Temperatures range from 200 to 240 degrees C. Total pressure was kept at 10 atmospheres. Hydrogen partial pressure and CO partial pressures were varied at over the ranges shown, with corresponding hydrogen to CO ratios ranging from 1 to 3. Deactivation experiments use the same conditions, except for the fact that the temperatures were raised from 250 to 280 degrees C. A Berti internal recycle reactor was used to obtain these data at low conversions, and under these conditions and with the monolithic catalyst, we hope to minimize heat and mass transfer effects and also temperature and concentration gradients across the catalyst bed. Here's some activity data representative of those that we obtained. The CO consumption rate in terms of total hydrocarbons produced and carbon dioxide produced are shown as functions of temperature and in terms of the reaction time for a given set of conditions. And you can see that as the temperature is increased, the rates on a weight basis also increase. And you can also notice that after just a few hours on stream, steady state is reached. And what can we get from these data? Well, let's first look at the selectivity. These data correspond to the 220 degree data set right here. Okay. Following an increase initially, the methane yield is seen to reach a steady state after 4 to 5 hours, as also do the C2 to C4, C5 to 11s, and the C12 to C14 fractions. We did see some alcohols, although the main product was ethanol. And so it was at these steady states that we were able to obtain reaction rates without the effects of deactivation. Now, looking first at the effect of the hydrogen partial pressure on the reaction rate, at a constant carbon monoxide partial pressure, we see that an increase from 1 atmosphere to 1.5 atmospheres pressure of hydrogen, we see an increase in the rate. And the orders of the deactivation are equal to the slopes shown here, ranging from 1.1 at the highest temperature down to over 2 at the lower temperatures. For similar conditions, except for the partial pressure of CO was doubled to 1 atmosphere, we did see still positive order, but the trend was from lower orders at 200 of 0.1 up to a maximum of 1 at the higher temperature. So we see that there's not a consistent trend there, and we'll be looking at that a little bit more later. Looking now at the carbon monoxide effect, keeping the hydrogen partial pressure constant at 1 atmosphere, we see negative effects. As the CO partial pressure is increased from 1/2 an atmosphere to 1 atmosphere, we see a decrease in the overall rate. And with the orders of reaction for CO ranging from -0.6 to -1.4. An increase in the hydrogen concentration to 1.5 atmospheres led to similar data, with magnitude of these values about half of what they are in this one. Activation energies were measured using Arrhenius plots, and we can see that there's still not a lot of consistency. We do see, however, that the maximum was reached at a hydrogen CO ratio of 3, and that with either a decrease in the hydrogen concentration, such as to this line along the bottom, or with an increase in CO concentration. And so there is some variation that we see. Well, what are the results? We do see a range when we look at each of the parameters independently. Looking at using an overall power law expression, we would hope to get a little better idea that includes maybe some of the interactions between those two, or between the parameters. And in fact, we see that the activation energy of 99 kilojoules per mole and the hydrogen order of 1.2 are just almost mean values of the range shown above. However, the CO appears to have even less of an effect on the reaction rate, giving an order of -0.2, which is even outside the range of that calculated independently. Well, we've seen that each of those parameters can vary quite significantly, and a power law expression does not really allow for variation in those reaction orders. So we're now going to look at a model based on elementary steps and see if we can develop a model which is consistent with the data, which does allow for some variation. What we see are the steps are CO adsorption and dissociation, hydrogen dissociation, stepwise addition of an adsorbed hydrogen to an adsorbed carbon species to form the CH, CH2, or CH3 species. Higher hydrocarbons are formed by insertion of a CH2, and hydrocarbons are terminated either by addition of an adsorbed hydrogen to form an alkane, or by the elimination of a beta hydrogen to form an alpha olefin. And the water and CO2 productions are shown here by reacting either hydrogen or CO with an adsorbed oxygen. Some of the approximations or assumptions that are made here, is that CO, absorbed CO, molecular CO, is the most abundant surface intermediate. It's also assumed that the propagation and the termination rates are slow compared to the other reactions. And in this respect, they are co-rate determining steps. The model is developed by making a steady-state approximation that the hydrocarbon of a given hydrocarbon or carbon number n, the rate of production is equal to the rate of depletion. And that depletion is either by propagation to a higher hydrocarbon or by termination to an alkane or an olefin. Now, what are the results of this model? Here we see the turnover number for C1, or methane, is a function of the water and the CO2 production rates raised to the third power, and we see the hydrogen and CO pressure dependencies. We also, this is a fraction here, not very clear, but in the denominator we have a term which is also a function of the carbon monoxide partial pressure to the 5/3 power. The K prime here is just a function of the various rate constants and equilibrium constants for the various reactions. Turnover numbers for higher hydrocarbons are represented by I, are functions of the propagation probability alpha and the turnover number for the next lower hydrocarbon. In cases where the rate constants are not independent of chain length, then this factor would come in, but in most cases that is assumed to be, those are assumed to be equal, so that would reduce to 1. And the alpha propagation probability is defined here is the rate of production of the higher hydrocarbon, or the rate of propagation over the sum of the propagation and the termination rates, both to paraffins and olefins. Bottom line is that the reaction orders have a range of values. The hydrogen order can vary from 1.1 to 1.5. CO can range from negative 1.3 to a positive 0.67. So CO can either have a positive or negative effect on the reaction rate. At this high pressure in this study, I've just shown that the hydrogen order was 1.2 as determined by the power law expression, and the CO was a negative 0.2. Some earlier work that we did on a similar catalyst at 1 atmosphere pressure and at concentrations of hydrogen and CO half of what were used in this study, we observed a hydrogen order of 1.4 and a positive 0.6 order on the CO. So in both cases, this model will allow for those different cases. Let's look now at deactivation. These data, what I've plotted here are deactivation runs that were made at the same hydrogen CO concentrations as the kinetic data, with the exception that the temperature was raised to 260 degrees. The rate, as I've plotted here, is the rate at a given time t over the maximum rate. And we see that with the exception of this one data set at a hydrogen CO ratio of 1, the deactivation rates are not significantly different. So we see that as with the kinetics, there is some complex, or the relationship between the deactivation rate and the reactant concentrations is not a simple one. The changes with temperature are a little more clear. We see as the temperature is increased, we see an increased effect or an extent of deactivation. Indeed, at 250 degrees C, in 48 hours, we only see a decrease of 40% of the initial activity, whereas at 280 degrees, in less than 24 hours, we're reduced to less than 10% of the original activity. Now, to analyze the deactivation data, we will be looking at and comparing the power law expression versus the generalized power law expression as developed by Dr. Fuentes. The difference in the two being that the generalized power law expression allows for a non-zero activity at large times. And as shown in this curve, it appears that the activity reaches somewhat of a level value around 0.2. And so we'll be looking at both of those to see if there is in fact any difference and which one fits the data better. Also included in these but not shown are the effects of the various reactant concentration in their dependencies. The results of the deactivation, we see a negative effect on hydrogen. This indicates that as the hydrogen partial pressure is increased, we get a decrease in the deactivation rate. And that is what we would expect, given that the hydrogen, more abundance of hydrogen would tend to react with the carbon and not allow it to go towards the deactivating type. The effect of carbon monoxide is, again, not very large, slightly negative to slightly positive, essentially zero. And we observed an activation energy of 74 kilojoules per mole. Let's look at now the two power law expressions. First of all, the power law expression with just the A, the activity raised to the activation order. First of all, we see that the hydrogen and the CO dependencies are just essentially mean values of over the range observed. However, take note of the high order of deactivation and the high activation energy. Looking at the generalized power law expression with A infinity values ranging from 0.1 to nearly 0.6 for different conditions. And this includes the analysis of all of those. We see not much change in the hydrogen CO effects, but we do see that the order of deactivation is reduced to nearly 1. And we see that the activation energy reduces from 274 kilojoules per mole to 51. And this is in very good agreement with experimentally determined values of 30 to 40 kilojoules per mole on nickel and ruthenium aluminum catalysts. And that value, those experimentally determined values, are for the transition of an alpha or surface carbon to a beta or polymeric type carbon on the surface of those catalysts. Well, what have we found? We've seen that the power law expression does not fit the data very well over the range of conditions. And as might be expected, power law expressions generally fit over a quite narrow range. However, when we used a Langmuir-Hitchwood model based on elementary steps, we were able to develop a model which did fit both the high pressure and the previous low pressure reaction study. We've seen that the generalized power law expression fits the deactivation much better than the power law expression. It gives us meaningful numbers, such as an order of 1 rather than 2 or 3 or even 5 or higher as determined by some of the individual data sets. And we expect that a model based on elementary steps for the deactivation process would fit data better, at least give some additional information than the generalized power law expression. And we attribute the deactivation of the iron catalyst to the formation of a beta or polymeric carbon on the surface. And we will be doing temperature program reaction studies to try and verify this. Thank you.
Questions? Yes. Could you step to the mic, please? Appreciate it.
Thank you. Rafael Espinosa from SASO. I find surprising that when you try to fit the kinetics, the exponents are a function of the operating conditions. But that usually means that the operating condition and changing somehow the surface of the catalyst. Now, have you been following the water gas shift activity or the ratio of water gas shift versus Fischer-Tropsch at the different temperatures?
We haven't been looking at the effect of that. We've been working at low conversions, so hopefully the effect of the water gas shift will be
Sorry?
it won't be a large effect.
Well, maybe you should look at the ratios of the water gas shift activity to the Fischer-Tropsch activity. Because even though the power law is not the best way to fit kinetics, at least it should do better than that. And if you have such a wide variation, it only means that something is happening to the surface of your catalyst.
One of the problems in doing that, and I can appreciate that, the water as produced in the high pressure work is much smaller than the CO2 production. In fact, the peak that we get on the chromatograms is a very broad, low peak for the water, and as such we are not able to observe and measure that. In the low pressure work, which I referred to earlier, there was a much higher water production as compared to this work. And in fact, the water and CO2 were more equivalent, and so we could do that on that work, but it'll be a little bit more difficult just because of the data that we receive. But I appreciate that.
I'd like to make a comment on that. I'll talk loud.
Yeah.
And that is that there's been extensive work done on methanation kinetics, on nickel, CO methanation. And in that system, done by several investigators, it's evident that the orders of reaction can vary over wide ranges for CO and hydrogen. And furthermore, the apparent activation energies can vary quite a bit, depending upon the conditions. So I'm not surprised by it.
I have two questions, I guess. First of all, I wonder if you could comment on your choice of an unpromoted versus a promoted iron catalyst for this work. And the second question was, if I recall right, the activation energy for deactivation was less than that for the reaction, for the Fischer-Tropsch reaction. And that would suggest then that higher temperatures favor the hydrocarbon-forming reactions in preference to deactivation. I guess my question is that consistent with what is observed in other systems?
Well, in looking at, let me answer your second question first. In looking at the data on nickel and ruthenium, the activation energy can change, but depending on where it is relative to the other one, it could be temperature can have a various effect. Increasing the temperature, let's see, it wouldn't necessarily mean that the hydrocarbon production would be favored at all temperatures. In other words, at higher temperatures, which is what we see, there appears to be a change in the magnitude of those two competing reactions, in that the deactivating type carbon is produced in preference to the hydrocarbons.
Okay.
And first one, as far as the unpromoted, we are planning to do some work with some potassium promoted. We did look at some of that with the lower pressures, and that's the next step here, is to look at with potassium promoted at higher pressures.
Okay.